Good morning, everybody. Today we have another Codeforces round. This one is 769. Teehee, here we go. Here's the contest. I forgot to register, but it's not rated for me, so it's not too bad. It's mostly just going to be practice, and we'll do our best on the contest here, and then afterwards we'll see how we do. I guess 15 minutes in we'll do the late registration or the extra registration. Okay, this is the previous Codeforces round, which we did quite badly on. Let's clear that out and try again. This one's Div 2, so, worst case should be, I guess, less bad. All right, here we go. Recently, students of the school 179 have developed a unique algorithm which takes in a binary string S as input. However, they soon found that if some substring T of S is a palindrome of length greater than 1, the algorithm will work incorrectly. Can the students somehow reorder the characters of S so the algorithm will work correctly on the string? Okay. So you can't have any 0, 0? The answer is probably not. Yeah, you can't have any 3 characters, so n has to be 2 or less. That's actually very, very interesting. All right, so if n's greater than 2, then this out no, else if n equals 2 and line 0 equals line 1, this out no, else this out yes. There we go. So that's problem A. Okay, we'll submit that in a bit. Let's move on to problem B. I guess let's run samples, I guess. We're waiting here. That's a really cool problem. But anyway, pretty interesting. It's finally been decided to build a roof over the football field of the school 179. Its construction will require placing n consecutive vertical pillars. Furthermore, the headmaster wants the heights of all pillars to form a permutation P of integers from 0 to n minus 1, where pi is the height of the ith pillar from the left. As the chief, you know the cost of construction of consecutive pillars is equal to the maximum XOR value, or the maximum value of the bitwise XOR of the heights of all adjacent pairs of pillars. The maximum value of the XOR of all pairs. Okay. Gotcha. Find any sequence of pillars with the smallest construction cost. That's just them being in order, right? Yeah. Should bring the numbers 1 to n in order. Oh, no, it's not. Okay. So just decreasing. So it's like you do. That's a good question. Good question. I don't know. Let's think for a moment here. So that we want to minimize the maximum bitwise XOR. Oh, but we're using all the numbers from 1 to n for sure. So Well, I guess, so if n is, okay, if n is even, then we can pair up all last values, or all, like, pair up everything. So we have like 1, 2, or I guess we have 0, 1, 2, 3, 4, 5, 6, 7. Okay. And then in the next layer we would have like 0, 1, 3, 2, and then oh, so now you have to match the 2 with the 4. So I guess 2, 4, 6, 7. No, 4 is with 5. 2, 4, 5, 7, 6. So are you always going to have to do the biggest power of 2? Let's think about that. Yeah, because you have to get from 0 somehow to the biggest thing. So it's always at least the biggest power of 2. And then if we have like less than biggest, and then we have 0, and then biggest, and greater than biggest, this will definitely work. Yeah, okay. I think that's fine, right? So what if the biggest is like the last thing? Yeah, that's fine. Okay. A is mu into a n. I equals 0 less than n x plus 8i equals I. This will already be sorted, so we don't need to worry about that. So then int biggest power of 2 equals integer dot highest 1 bit of n minus 1. What if n is, yes, this will be at least 1, okay. So then for int I equals biggest power of 2 minus 1. I is greater than either 0 minus minus. O dot print line I plus a space, not print line, just print. And then for int I equals biggest power of 2. I is less than n I plus plus. Print this, I dot print line. And then we don't need this. Yeah, 1, 0, and then 2. 3, 2, 1, 0, 4. So all of these things don't have this biggest power of 2, so yeah, they'll all be less than 4. Yeah. This has 0, 4. Oh, okay, it's exactly what I had. Okay. Yes, looks good. Let's move on to C. Strange test. Igor is in. Oh wait, can we register yet? We can. Good. we got A. We got B. Let's get C. All right, Igor is in 11th grade. Tomorrow he will have to write an informatics test by the strictest teacher in the school, Pavel Deniaskovich. Did I get that right? No, Deniskovich. Okay. Igor knows how the test will be conducted. First of all, the teacher will give each student 2 positive integers, A and B, where A is less than B. After that, the student can apply any of the following operations any number of times: A++, B++, or A or equals B. To get full marks on the test, the student has to tell the teacher the minimum required operations to make A and B equal. Okay. Igor already knows which numbers the teacher will give him. Help him figure out what is the minimum number of operations needed to make A equal B. Oh, they're both 10 to the 6th. The sum of B will not exceed 10 to the 6th. Good, this is very important. Okay, so we're gonna do some BFS from B to A. Sum of B, but not, oh, A is less than B. Yeah, so you do a BFS from A, basically. So this is the only time you'd overshoot. And this is, yeah, okay. All right, so we're given A and B. And then we need int double or int array distance. Just at 0 or just at A equals 0. So then, do these only increase? I guess we'll just do a BFS here. Yeah, okay, so int ants will be B minus A. Spits out the answer. And then this will be int at, will be BFS dot remove first. Int cur dist will be disted at. So then, okay, so int2 equals, we can go to at plus 1, or we can go to at or b. Okay, so if 2 is greater than b, ants equals math.min of cur dist plus 1 for this operation, plus 2 minus b, or the answer. That's always an option. Oh wait, we can also increment b first, I suppose. We can increment b first. So, yeah, that's a good point. So this isn't like, we can't strictly do a BFS, I don't think. Or can we? Let's say we're at this. we're trying to get to this. Yeah, so you want to increment b, and then you want to make them equal. So we do want, okay, so the idea here is we'll do a BFS from A, and then also, like, just for each of the things. Well, I guess, wait, so we can turn on any subset of the bits that we want. At any point. Okay, this is the difficulty jump, yeah. Okay, we can do it still though. So we're gonna do this BFS from A. But it's tricky because we can OR with this B. Yeah, and then, okay. So, and then like see how close to B we can get. So then we need like this DP of like value equals min number of turns to get here. So each operation we can do is subtract like value minus minus, or we can turn off a subset of bits. Can it be any subset? I don't know. So like one observation is that the only values these will end up equal to is like stuff between A and B times 2. Well, maybe it's not that much bigger. Like for this biggest bit, oh, interesting. Yeah, that's interesting. So if B is like a power of 2, then you can like OR equals like one step before, and then increment A. What if we brute force the ending, like the final value of B? What happens if we try this? So now we know B goes from like X to Y. We need to get A from A to Y. So we can't ever make A too big. But we always want to do the OR operation first if we can. Would we want to do the OR operation multiple times ever? So we're gonna have like some bad elements, I guess, some elements that are good that need to stay good, and then these. So these need to be zeroed out. Okay, so yeah, we need to find the biggest element that needs to be zeroed out, right? So that would be this here. And this is a tough problem. Let's read D. New Year's concert. New Year's is just around the corner, which means that school in 179, in school 179, preparations for the concert are in full swing. There are N classes in the school, numbered 1 to N. The ith class has prepared a scene of length AI minutes. As the main one responsible for holding the concert, Idnar knows that a concert has K scenes of length B1 to BK minutes. And the audience will get bored if there exist two integers L and R. And the GCD of these things equals the size of the range. You will get bored if the GCD equals the size of the range. To avoid the boring audience, this person can ask any number of times that the teeth class make a new scene. What is teeth? What is T? Oh, that's not helpful. Okay. That the teeth class, so that he can, make a new scene D, minutes in length, where D can be any positive integer. Thus, after this operation, B sub T is equal to D. Note that T and D can be different for each operation. For a sequence of length B1 to BK, let F sub B be the minimum number of classes this person needs to change if their scene wants to avoid having any ranges with the same GCD as length. He hasn't decided which scenes will be allowed for the concert, and he wants to know if the value F for each non-empty prefix of A. In other words, he wants to know F of A1, F of A1, A2, and so on. All right, so for this, you need to change this thing, because it's not happening. For this one will be fine, because you'll just make it infinity. Oh wait, so it's got to be something. Okay, so then for length 2, you want this one to become like a 3, I guess, or a 5 maybe. A really big prime, that way it won't matter. Yeah, so you always want a really big prime, right? A really big prime is always optimal. Because like, on its own, it'll be really big, but with anything else, it'll be 1. And as soon as it's with something else, your range is at least size 2. So you just make it like 10 to the 9th plus 6 or something, or plus 7. So 1, we make it 10 to the 9th plus 7. If we have 2 things, we don't necessarily just want to change this first. Oh, we do. Yeah, we do. Yeah. So then we have 10 to the 9th plus 7 and then a 4. You always change the last one, right? Yeah, you might as well. Then you have a 2. So the GCD of this is 2. Yep, this is way easier than C. I can tell you that for sure. Okay. So we'll just have a segment tree. With range GCD. Or we don't even need that, I guess. Yeah, that'll be log squared. Well, should be fine, probably, but okay, it's a little annoying to implement. We can do it with binary lifting, or we can do it with a segment tree. We can also walk the segment tree if needed. Yeah, with binary lifting, we only change the last element anyway. So I guess we'll just do this. We'll do, this will be 20 by n. Yeah, okay. So we'll figure out which, or I guess this will just be I suppose. So then if A at I equals 1, then A at I equals, oh, we should probably have an OK function. Static Boolean OK. It would be int I, int val, int array lift. If OK at it is any, hang on, it's any continuous range, yes, okay. So if OK at I with A at I and lift, if this is OK, then we'll just continue. Well, if it's not OK, then A at I equals 7. Then we need GCD. Okay. So we're good here. I now need to build this. So for int E equals 1. E is less than 20. E plus plus. So lift at 0 I will be A at I. Okay. Lift at E I will be GCD of lift at E I minus 1. Okay, so then int range start will be I minus 2 to the E minus 1. So if range start is greater than 0, greater than or equal to 0, you do this, else lift it ei equals lift it e minus 1 I. So e minus 1 I minus 1, or e minus 1 I, and lift at e minus 1 range start. Okay, so this is fine. Excuse me. I think we should be good then, right? So yeah, this builds this, and then we just need, okay, all right. Okay, so while lift, yeah, I guess we'll just modify these two. So this is at, and this is the GCD. So in exponent equals 0, so while lift, or I guess while GCD of GCD and lift at exponent plus 1 equals the GCD, then exponent plus plus. Okay, GCD is less than 20, or I guess exponent less than 19. If exponent equals 19, then return true, will be okay. All right, so we need the new ending, I guess. Yeah, we need to find when the GCD decreases. Okay, I'll admit this is a little bit harder to implement than I initially thought, but the idea is really straightforward. So I guess it's understandable why an LGM is getting it instantly, but nobody else is. Oh, actually, never mind. A bunch of people are. So we'll get this in a minute. And then C is confusing. But man, look at this guy. He's consistently one step ahead of the curve, but just having difficulty with C. What is this? Performance. Oh, interesting. That's kind of cool. Plus 300. Well done, man. Well done. Okay, just C through D. It's 3,000 rating. Anyway. Yeah, so we need to find all of the places the GCD increases or decreases. Should this just be its own method? Oh, we can just we can just binary search, right? Yeah, let's just binary search. Because these GCDs can overlap here. Alright, so let's not worry about this. So if okay, so then int size would be r minus l plus 1. So if size equals 1, return lift at r. Return 0r. Otherwise, int our, I guess, max 1 bit will be integer dot max or dot highest 1 bit of size. Int exponent will be integer dot number of trailing zeros of max 1 bit. And then we'll return GCD of lift at exponent r and lift at exponent r minus max 1 bit. Oh, okay, so r minus size, this will get, so l plus max 1 bit. Is this right? So let's say L is something, max 1 bit is 2, L plus 2 minus 1. Yeah, that's what we want. Okay. Okay, so we have range GCD. Okay. It would be helpful to do this first, I think. Or do it first as well. Alright, we'll handle this in a bit, but yeah, so, okay, so we should be fine here. So this is all good. Now what? Now we need this part. So we need to find all the times the GCD changes, which will be log n times at most. So this will be int r, int GCD, and array lift. Okay, so int L, or int min L equals 0, max L equals R, min L is not equal to max L. Int mid L equals min L plus max L over 2. If range GCD of mid L to R with lift is not equal to GCD, that means we've gone too far. So min L equals mid L plus 1, else max L equals mid L. And then return min L. Okay, so this does that. So this will be in R. In L will be get leftmost time GCD is X. Oh, I guess we want this mod GCD. Okay. GCD is X. So, we'll go from R to what GCD? To the GCD? And then okay, so then well, L is not equal to -1, I guess. L minus minus. And then GCD equals GCD. Oh, equals, I guess we'll just say range GCD of L minus 1 to R. That is not equal to 0. From L to R with lift. Okay, this will be our new GCD. And then we'll skip to the good part. Okay, so then static Boolean check invalid. So we'll add int R, int min size, int max size. Okay, and then right L, int left L. Check invalid from R to L. And false. So the right L will be L. Okay, so int, oh, we also need the, well, I guess we don't. So int GCD equals range will be range GCD from left L to R. And min size will be right L, or it'll be R minus right L plus 1, and max size will be R minus left L plus 1. So if GCD is greater than or equal to min size, and GCD is less than or equal to max size, then return true. It is invalid, otherwise return false. Oh my goodness, we're done. Okay. Oh wait, we're not done. All right, what are we doing here? Oh, single test case? Okay. 1, 2, 3. Zero, 1 to 1, 1. Those are different. 0, 2 to 2, 2. That's not right. is this? So range GCD of J to K. Okay, GCD from 0 to 0 is 0, but that's too early. GCD from 0 to 0 is 1. Yep. Okay. GCD from 0 to 0 is this. GCD from 0 to 1 is this. GCD from 1 to 1 is this. That's all right. Okay. So this part works. Okay. Then when we have okay. So first, leftmost time GCD is 4 is not 0. My GCD right? B of A my B. Yeah, I think that's right. So why is this? The min L equals 0. Yeah, max L equals 1. Okay, so this is 0. So if range GCD of this modulo 4 is equal to 0. What the heck? What is the GCD? If 1 modulo 5 equals 0. It definitely does not. Oh. Should be not equal. Two, 1, 4. Yeah, okay. 1, 1, 2. Ends in a 2. Okay. 2, 2, 1, 1, 1. Yeah, it seems right. Ooh, it took a while, but I knew that. All right, good. Got D. How are we doing?
No answer. A-E1
Not great. Okay. Yeah. So lots of people are getting C. Maybe we read E1, but then consider C. Okay. Oh wait. So this thing is quite cool. We can see how people are performing, I guess, right? People around us. Like we don't see. What was I? I was like 270. We don't see what we do, but we can see what the people around us, how they're doing. If this loads. Yeah, so like 2100 is the rough performance. Yeah, so this is worse than what we're doing. So we're performing below average. There you go. Well done. Well done. Look at that. Very cool. Okay. Distance tree. This version of the problem differs only from the next one and the constraints of n. So n is 3000 here. A tree is a connected, undirected graph without cycles. A weighted tree has a weight assigned to each edge. The distance between two vertices is the minimum sum of weights on the path connecting them. Okay, yes. So we have a weighted tree. I see. We're given a weighted tree with n vertices. Each edge has a weight of 1. Denote dv as the distance between vertex 1 and vertex v. Let f of x be the minimum possible value of the maximum dv you can temporarily add an edge with weight x between. This is the minimum possible value of the maximum. Wait. So the minimum possible value of the max of the distance to any node you can temporarily add, if you can temporarily add an edge of weight x between any vertices A and B. So we're interested in the distance between the root and some node. We're going to add an edge of weight x. We want to know how big this thing gets. After the operation, we don't have a tree. We have a tree with an extra edge. Okay. I'll be right back. But it doesn't seem too hard. how many points do I get for this? As many as I do for C. Well, then might as well solve this. The only edges you'd ever want to add are the edges between the root and some node, right? Like, yeah. So there are only order n of those edges. Oh, but you also have this x issue. So, okay, we have some edges we might add. It's kind of like BFS, but you can also start here. Start it like this other place. So it doesn't really need to be Dijkstra's. Is it binary searchable? Might be binary searchable. So leaves are like the only real constraint, right? Yeah, you have some leaf constraints. So like every time you have a leaf, there's the constraint, like, so, okay, first of all, one end will always be the root. We know that. Then every time we have a leaf, we have this constraint that like it needs to be like x or closer to us. So we have a bunch of leaves and a bunch of these constraints. They all need to be in a path. They might all need to be, we might have even better. Like all, ooh. X needs to only move down. What was the other problem I'm choosing not to solve here? C? Oh yeah, this. Okay. These can't both be hard. Both of them seem somewhat easy. Let's get some paper. Purple? Color of the day? What do you guys think? Silver is not too helpful. How about purple and black? All right. So yeah, what's happening? We've got like a tree. Ooh, I hope this isn't flickering too badly. Does that solve it? Kind of just makes it worse. Okay, oh well. I'm sorry if anybody is subject to seizures and I just caused you to die. That was not the intention. Just trying to make a cool YouTube video. Okay, so this gives us some constraint, like it's got to be here or lower. Oh, it gives us like a range of nodes. It's like you have to pick one of these nodes. But it's not like that, because you can also pick, it also includes this node here. And then, yeah, so then you can have something like this. It really also includes this one too. Yeah, so like, let's say that we have another node up here. So let's say x equals 1. What is the... yeah, so let's say x equals 1. And then our answer... and then answer equals 4. So a possible answer here is to do this. So then we have 1, 2, 3, 4. 1, 2, 3, 4. Yeah. Okay. It's an odd case. So we want like the distance to the near, or to the... yeah, I don't know. Let's look at C. So C is strange test. So we have A plus plus B plus plus, or A or equals B. And then we literally just want, yeah, we want A to equal B. Okay. In min ops. So what do we do? Yeah, it seems pretty tricky to figure out how you'd go about doing this if you don't know what B ends up being. So maybe like we brute force B in B to like next power of 2. Okay, so we know the final B. Which means we know what things we can OR with. Okay, but we know what B ends up being. So like there are, so we can like, yeah, we can never get too big. Because if we pass B, we've made it impossible for ourselves. So we can't ever, yeah, we can't ever exceed the final answer. Which means oh, this is annoying. So you've got like, do you ever want to A++? You might have to. You would always rather do this if you can. Yeah, okay, so we know what we're going to. Yeah, we just have to get A to like B prime. And then we know how to get B here. This is like easy. So this is just the hard part. How do we do this? So let's say like 1, 0, 1, 0 is the target. And let's say we start at 1, 0, 0, 1. Okay, we also need the minimum thing we're allowed to OR with. So all the way up to this. That's a lot of choices. Will you ever OR multiple times? I don't know, it's not, maybe. Maybe you do. Is it just get A to a submask of B? Is that it? Hmm. Because if that's the case, it's super easy to implement. Seems like it wouldn't be the case. Why might it be? So let's say A is a submask of B. Then it takes one move. So then we're saying if A isn't, then we never OR. If A isn't a submask of B, if that means we never OR, if that's true, that means that it's always bad to introduce a new bit. I don't think that's true. I don't think that's the case. Maybe it's the case. Okay, well, if it were the case, how would we even implement it? Well, one thing to be a submask of another. Oh, so you know B prime. What's the closest, like, the smallest submask? Bigger than A? Greater than or equal to A? Yeah, so it's for each bit, take it if we can. Oh, like don't take each bit. Yeah, okay. Or in other words, take each bit if we have to. No, that makes it confusing. Because later on you might have other constraints, so you don't know if you have to. Okay, so I still feel like this isn't true, though. I don't know. I guess we'll try implementing it. Okay. Let's try it. Okay, so we have n equals b. Answer is b minus a. Yeah. Okay. So occur will be n minus b. Then plus 1 for the, oh, okay, so if n is not equal to b, for total moves plus, and then we need to add the a moves. Okay, so int end mask equals end. Yeah. Then, wait, the only reason you would add b, it's possible this is true. Yeah, I think it might actually be true. Okay, so the end mask is end. So while, or what do we want to do? So we want to remove, or don't take each bit if we can. Yeah. This is greater than or equal to a, then n mask minus equals 1 to the bit, or 2 to the bit. So remove these bits if we can, and then what we're left with is the best we can get. So then per total moves plus equals n mask minus a. Or the shot. No. Why is 1, 3, 0? How is it 0? Oh, this should just be per total moves plus, yeah. Seems like an appropriate difficulty, but I still have no proof at all that this is right. Okay, guess it is. We will leave that to faith, because I have no proof. All right, how are we doing? Very badly. Okay. Yeah, let's go for E1 here. Man, nobody's doing this contest. Why not? Why not? Rainbow is crushing it. Well done, Rainbow. Yeah, let's see. What is E1? What's going on here? Only in the constraints on N. So we've got a tree. We need to add some edges to this tree. And oh, we're adding one edge to the tree of varying weights to make it a Cthulhu graph with minimal diameter. No, not diameter. Distance to node 1. Minimum distance to node 1, huh? Why? Oh, that's kind of cool. Look at this. So we can let's only consider the leaf nodes. Then for each leaf node, we have like a min depth allowed and max depth allowed. Oh, that's kind of cool. Look at that. Yeah, so here, basically what we're doing is we're saying value equals the max of AI or X, which is a segment tree beats operation. And then we need every leaf to have the same, oh, but this is annoying because, yeah, so this doesn't actually handle some stuff. What about this? This is kind of different. Okay, yeah, because this one, we can also pick this. So maybe this is difficult. Okay, what if instead of doing that, we consider which node we brute force? Or which node we pick, yeah. What happens there? So if we brute force the node we pick, then every node has a min, this is probably it. It's one of these problems. I can't stand these problems. Okay. Yeah, I read about these. Okay, so everything has a min of, or wait, so okay, you've got a couple choices. So you've got some farthest thing. Well, this will solve, we're not getting E2 at this point probably, right? So this will give us, we can get, we can brute force the node, what we pick. And then we can like BFS to everything else. So we know its distance. Yeah, and that's all that matters. So I mean, we were considering, so this is n squared here. Okay, and then we just need to say, for this value, if we have this value and we pick this node, then we get whatever. Yeah. Okay, so certainly something we can do. BFS from some node. We'll get nodes. And then whoa, magic. Okay. array deck integer node DFS new array deck DFS.add from DFS is empty node next equals DFS.remove remove last. Then we'll say for node nn in next.adjacency if nn.dist equals -1, then nn.dist equals next.dist +1 dfs.add and oh, okay. From .dist equals 0. Okay, so that's that. Awesome. Node array nodes. This new node array n. Then has input given just all the edges. Alright, so we've got this, so then BFS from nodes at 0, pass in nodes, for node n in nodes, nn.dist from root equals nn.distance. Okay. So then static, or I guess we'll have int double array, ants if we pick x, or if we pick u for x equals new int array n by n. Wait, what is, yeah, okay. So so ants table at u x equals ants lower bound if we pick u for value x. We are not fast enough yet. We're not there yet. Okay, so each node needs to have like each node has a ceiling. So this is x, and then this is the farthest. So after a certain point, if x increases, this is this. Will it look like this? Is this the right answer? So we have like a node and a distance value, or we have like a pair of nodes. But there are n squared of these already, so we have to do this in like constant time. So we can be like, hey, your pair is gonna look like this. Yeah, then what? Oh, also at a certain point, like, it just doesn't affect you either. Yeah, so everyone has a bunch of these. We want the max of all of them. So this is the point we're interested in. This is annoying. What if we have one of these? What if you've got, so, yeah, so you can have this, maybe. That's one graph. And this is another graph. Is that possible? I think it could be possible. Oh, it almost certainly is possible. Otherwise, it'd probably be easy. So we get a bunch of, okay, yeah, so we get n squared graphs. Then we need to say, yeah, n squared graphs look like this. Then for each x, but we have a graph for every, okay, for a given node, oh, this is just for one node. There's no way it looks like this. What? Okay. How much time do I have? 11 minutes. How do you do this problem? So this node Okay, this node here. What does it look like? For x equals 0, has a bunch of things. So it's got itself. It's got two things of size 1. It's got, it's two things of size 0, 3 things of size 1, 2 things of size 2, and then 2 things of size 3. Okay, what if x is 1? Now it has 1 thing of size 0. It's got 3 of size 1. No, it's got 2 of size 1. 1, 2 of size 1. Oops. Of size 2, it's got 1 of size 2, 2 of size 2. Size 3, 1, 2. And then 2 of size 4. Okay, so for a given node, you've got a bunch of things that look like this. They start at, like, the start is the distance, okay, the y-intercept is the distance to you, and then the max is the distance to the root. Yeah. So you've got a bunch of these things. Okay. So that's what this looks like. So each node has a bunch. Okay, so yeah, we can do this. Can we do it? How much time do we have? 8 minutes. Maybe, actually. We'll be close. Okay. Graph array, graph for node equals new graph. All right. Okay. Or it's the graph for the pair. All right, so for node from equals 0, erase node from in nodes, BFS from nodes. Okay. For node NN in nodes, graphs for from graphs for node at from index equals new graph. The y-intercept will be from that distance, and then this will be from that distance from root. Yeah, what's up? Oh, dot add. Okay, so we got this stuff. Yes, this will be nn that distance. This will be nn that distance from root. Yeah, okay. All right, so then for each graph, n plus 1. Okay, multiple test cases, yes. Sum of n is less than 2,000. We're fine. How much time? 4 minutes. Might be enough. All right, so then we need to, for node nn in nodes, we need to arrays.sort graph by what? By we want the highest. Yeah, we want the graph sorted by. I guess we want the highest one, right? Sort the graphs for node at okay, so for an offset equals 1, offset is less than n plus 1, offset is plus. Okay, so while end at is less than graphs. While end at is less than L dot size and L dot get end at dot max is less than offset plus end at dot y-intercept, then best equals math.max, so best and go to the next one. All right, and then okay, well, are we even right? No. I mean, we're surprisingly close, but okay. Anyway, yeah, okay. Decently fun contest. Would recommend. I mean, I enjoyed it. I think I didn't really have any problems with anything other than no idea why C is right. Yeah, it's alright. It's alright. Can't complain. Well done, Rainboy. And well done, Neil, as well. Neil crushed it. I guess let's discuss solutions here, as we do. So, yeah, let's talk about problem A first. ABC. Okay, so this is really cool. You've got some binary string of zeros and ones, and you want to reorder some of the characters so that it has no palindromes of length greater than 1. Obviously, if it's got one character, it'll have a palindrome of length 1, because anything of length 1 is a palindrome. But you want no palindromes of length 2, no palindromes of length 3, no palindromes of length 4, etc. And a key thing to notice here, which is very important if you want to not have any palindromes, is that if you have any palindrome of length 3, right? Or let's look at like abacaba. Obviously, this has lots of palindromes. The whole thing's a palindrome. This is a palindrome. ABA is a palindrome, right? But if you have this palindrome that's of length longer than 3, you're always going to have a palindrome of length 3 inside. So any odd length palindrome has the palindrome of length 3 in the middle. And any even length palindrome, sure, the whole thing might be a palindrome, but you have a palindrome of length 2 in the middle. So we only need to worry about palindromes of length 2 or 3. And if we only have zeros and ones, well, the first thing, it doesn't really matter whether it's a 0 or a 1, because we could just flip everything. So we'll say it's a 0. The next thing, it's got to be a 1. If we put two zeros together, that's a palindrome. So we need a 0, and then we need a 1. Okay, so we got the 0 and the 1. What is this? Well, it can't be a 1, because then we'd have 1, 1, and it can't be a 0, because then we'd have 0, 1, 0. So there really is nothing we can do at this point, which means the longest string you can have that you can't, like, that's even possible is just a 0 and a 1 or a 1 and a 0. So the code for that is incredibly easy. Code for that just looks like this. It's length 3, it's impossible. Or if you have two things that are the same character, it's impossible. Otherwise, it is possible. Okay, that is problem A. Let's talk about problem B. Roof construction. Okay, so yeah, in this problem, you have the integers from 0 to n minus 1. You want to make a permutation of them. And you want to find the smallest that you can make the maximum bitwise XOR between adjacent pillars. Let's do an example. Okay, so let's say the numbers that we're dealing with here are, let's do the example they give here. So 3, 2, 1, 0, and 4. So if we write these in binary, we'll get 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, and 1, 0, 0. Okay, so if we look at these first two numbers, their XOR is going to be the bits that one of them has and the other doesn't. So they both don't have the first bit, so that's a 0. They both do have the second bit, so that's also a 0. and then only one of them has the third bit, so it's a 1. So look at these two. They neither have the first bit. One of them has the second bit, and one of them has the third bit. Let's look at this one. Neither has the first bit, neither has the second bit. One has the third bit. And let's look at this one. One of them has the first bit, neither have the second, neither have the third. So if we turn these numbers from binary back into base 10, we get 1, 3, 1, and 4. And the biggest here is 4. So we want to make this 4 as small as possible. That's what the problem's asking. If we change the order of the elements in the top. Okay, so that's the problem. Now, how do we do it? Well, the key observation here is that if we look at this bit here, we're going to have some things that have a 1 on this bit, and we're going to have other things that have a 0. Which means no matter how we order these, eventually we're going to have something with a 1 next to something with a 0, because they both have to exist. So we know the smallest we could possibly get this is at least 4. It's at least 2 to the 2, right? And since it has to be 4, the question is, can we just make it equal to 4? And yes, the answer is we can. One of the ways of doing that is we can put a 0 here and then a 4 here. We can have stuff bigger than 4 here. So this is all stuff between, it's got to be greater than or equal to 4 and less than or equal to, or strictly less than 8. Because then it will have the 3 digits. The biggest thing it'll have is the 4. But none of these things in here will have the 4 bit, right? It doesn't matter what you put here. You can put like a 7 here. You can put a 6. You can put a 5, right? All of these things will have the 4 bit, which means like both of them will have the 4 bit. We'll never have the case where exactly one of them has it. And then over here, similarly, we can do anything that's less than 4. So we can do like 1, 2, 3, and then the 0 if we want. So all of the adjacent pairs over here will be less than 4. All of the ones over here will be less than 4, and then this one will be equal to 4. And we know 4 is the smallest the answer could possibly be, so you can't do better than that. All right, so yeah, that's the solution to this. This is probably not the cleanest way of ordering them. I just did 3, 2, 1, 0, and then 4, 5, 6, 7, 8, 9. Implementation looks like, nope, on problem B. Looks like this. Whoa, whoa, okay. Yeah, implementation looks like this. We've got just the n they're giving us, and then they give to us, and then we have numbers less than it down to 0, and then bigger than it up to n. And that's it. There we go. That's problem B. Okay, on to problem C. Do I know how to do this? No, but I can explain what the solution is. I can't prove it. So here's the idea, or the problem is you've got 2 variables a and b. You can do the operations a++, b++, and a or equals b. You want to make a and b equal to each other, and you're guaranteed a starts smaller than b. Okay, so the question is, how many operations does it take if you pick the right operations in the right order? Okay, so here is the magic part that I haven't proven, which happens to be true. If you have a proof, feel free to leave it in the comments. Or I'm sure it'll be in the editorial as well. But the idea is you only do operation number 3 once, and it's also the last operation you do if you do it. So yeah, so basically you're either going to increment a bunch, increment b a bunch, and then or equals a, just like copy the bits from b into a, and then they'll be equal, or you'll just add to a until it equals b, and that's it. I don't have a proof why that's true, but it's true in samples and it passes pretests, so it's almost certainly true. Okay, so if that's the case, then how do you do it? Well, if that happens to be true, the problem's actually pretty easy, because if we wait, how do you do this actually? Let me think. What did I do? So if we know what b will end up being, yeah. So if we know what b is at the end, then we just need to increase a to be a submask of that. So let's do an example here. Let's say we know after doing a bunch of operations, b will be this. So this is what b equals. So we know a needs to be some submask of this thing. So maybe a equals 0, 0, 1, 1, 0 initially. So if this is b and this is a, what's going to happen is a will be some of these things, but a will only be we'll add to a until it only has bits that b also has. In particular, if we're only doing operation C once, then we know a can't have any bits that b doesn't have, right? So we're going to have to get rid of this bit. And we also won't be allowed to have this bit or this bit. Because once we do the operation to make a equal to b, or have a take all of the bits that b has, if a is then bigger than b, then the b that we end up having won't be the same as the a that we have. So we can't have any of these bits, which basically means we're going to have some submask of this is what a is going to be. And we want this, once we know what submask a is going to be, we have to increment a to get to that submask. So we want the submask that a is going to be as small as possible. That way we spend as few turns incrementing a. So if we look at the submasks of b, we have obviously equal to b. Then we have this one, and then we have this one, and obviously we have all zeros. Now we can never make a smaller, and a is currently equal to this, which means this one is too big and this one's also too big. So of the two that are left, we want to pick the smallest one, which will be this. So the answer will be, we'll spend one turn to do the operation 3, and then we'll spend another turn, or we'll spend this number minus this number turns to do this. So we have to do this as well. Yeah. So how do we do this in faster than a slow amount of time, right? Because it's already we're already brute forcing what b will end up being. So how do we make a equal to b fast? Well, we can go, if we know what b is going to end up being, in this case it's 1, 0, 1, 0, 0. So if we know what this is, we can iterate from the biggest bit to the smallest bit in b and see if we remove this bit, will the number without this bit still be at least as big as a? Will removing this bit make it too small? If it does make it too small, obviously we can't do it. But if it doesn't, then we can remove this bit from b. So that's the idea. We're going to go from biggest to smallest and remove the bits if we can. Otherwise we won't, if either they don't exist or we can't remove them. Finally, we have to be brute forcing which b we choose for this, right? Because we don't know how many times we're going to increment b. And you might be like, well, there could be, how do we know this could be a very big number? We can make the observation that we don't want to introduce any new powers of 2. There's never that's never helpful. And since we're never going to be introducing new ones, that means the maximum number of times we would increment b is we would double it, right? We'll never double it, but 1 less than doubling it, or maybe 2 less than doubling it, would be the maximum number of times we would increment b. So we brute force how many times we increment b, And then after that, we say, let's assume A is going to be a submask of B when we apply operation 3. How many times do we have to increment A to make it a submask of B, which we can do by greedily finding the smallest submask of B bigger than A. That all made sense. Okay. What does the code look like? So just like I said, nope, wrong code, C2. So just like I said, we're going to brute force the end B value. I'm going to call it end here. And this goes from B to B times 2. Because we don't want to introduce extraneous values of 2. That'll never, or extraneous powers of 2. That'll never help us. So one way of doing this is we can just walk directly from A to B. And then we don't have the extra operation 3 cost. So we have to, that's one possibility we have to account for. Otherwise, we will be copying the bits from B into the bits from A. So this will happen. And then we have to increment B a bunch of times to get it to this end value. So we'll do that first. We might as well. And then finally, we need to check which bits we can remove from that. So we don't have to increment A as many times as possible. So yeah, that's what this does. This finds the smallest submask of B that's bigger than A, or equal to A. Yeah, I don't have a proof for why you only do operation 3 once. So that would be cool to have. All right, next, let's look at problem D. I know how to do D, so we'll talk about that. And I also know E1. So we can talk about that in a minute too. All right, so for problem D, we're talking about New Year's here. We have an array, and we want to change some elements in the array in such a way that there are no continuous ranges in the array that have the same GCD as they do length. So we want for every continuous range in the array, we want the same, or we want the length of that array to be different from the GCD. Now, not only do we want that for the entire array, but we want to know that how many things we need to change for every prefix of the array. I guess we'll look at an example here. So if you have an array of just size 1, and the element there is 1, there's the subarray of length 1, and the GCD of just 1 is just going to be 1. So I said 1 probably like 5 times in that sentence. But the point is, you don't want the length, which is 1, to be equal to the GCD, which currently is 1. So we have to change this element. So we'll change it to something else. Maybe we'll change it to 2. Okay, let's look at the second example. In this case, the array is 1, 4, 2. So this first element, we're going to solve it for just this prefix, and then for the 1, 4, and then for the 1, 4, 2. Let's look at just the 1. Well, we have to change it to something, so we can change it to a 2. Okay, let's look at the 1 and the 4. So the GCD of these two elements is fine, right? So we wouldn't have to change anything. The GCD of the two elements is 1, and the length is 2, so that's fine. The problem is, we have to change this 1 to something else, because a subarray of the first 2 elements is just the 1, and the 1 has size 1 and GCD 1, so we have to change the 1 still. We can't change it to 2, because if we do change it to 2, then the GCD of these first 2 elements will be the GCD of 2 and 4, which is 2. And the length of this is also 2, so we can't change it to 2. So let's instead make it 3. If we do that, then that's fine, because the GCD of 3 and 4 is 1. So that's the idea. For this, we could change the first element to 3, so that would be changing 1 element, and it would make the prefix of size 2 work. Yeah, also I guess I didn't talk about this, but the GCD of just the second part would be 4, and the length would be 1. So that's okay too. All right, finally, let's look at the entire thing. So we could change the first element to something. We wouldn't want to change it to 2, because that would break this. 3 would be fine in this case. So we could change this element to 3. And we have this problem here. So with this 4 and the 2, we can't have both of them be multiples of 2, because then the GCD of this array would be 2. So we could change this last element here to a 3 as well. So if the array was 3, 4, 3, that would be perfectly good. All right, so that's the problem. Hopefully that made sense. Let's talk about the solution now. So the first observation here is that you don't want to change stuff to a small number because, like you saw earlier, it might wind up getting in your way later on, and that would be annoying. So we'll avoid that when possible. And in fact, what I claim is the best number to change something to is 10 to the 9th plus 7. So it's a really big prime number. That's the idea. Why is that? Well, we're never going to have 10 to the 9th plus 7 elements, right? So if you have 10 to the 9th plus 7, we'll never have that many elements. Also, if this number ever gets decreased to something else, it'll get decreased to 1. Since it's a really big prime, it doesn't share any factors with anything other than itself. That's the definition of a prime. So if it gets decreased, it'll be something very small. It'll be 1. But also, if it is getting decreased, that means there are at least 2 things in the array. So it will never cause problems if you change a number to 10 to the 9th plus 7. Because if the GCD is 10 to the 9th plus 7, that means there won't be 10 to the 9th plus 7 things in the array. And if the GCD is 1, that means there are at least 2 things in the array. So that's the idea. Okay, so we know changing something is the same as just saying, once we change it, we can ignore all arrays that include this element. So that's for changing it. Now the question is, which things do we change? Well, since we're looking at like every prefix, we can always change the last element in some array if we see a bad subarray. So if we look at just the first element, if we need to change it, we'll change it. If we look at the first 2 and the second also breaks, that means we need to change the first element regardless, right? Because the first element wasn't hurting us. And we also need to change the second element regardless, so we'll do that. But if it's possible we need to change one of the first 2 elements, then we'll wait to do that until we have something that forces us to do that. So we'll be greedy with it, and it turns out that works. And it's provable that works. Like, it should be pretty obvious that it works. I won't really explain. Maybe I'll explain why. Okay, so basically, if we look at the entire array on its own, we'll have like a bunch of elements here. And there are a bunch of ranges that are bad, right? So maybe this range is bad. Maybe this range is bad. Because this has a GCD of 2 and a length of 2. This has a GCD of 3 and a length of 3. Maybe this has a GCD of 1 and a length of 1. So what we have to do is we have to kill some of these elements so that we hit every range at least once. So we can kill this element here and this element here. And the logic here is the same as for gassing bunnies. So this is a problem that I've talked about, but basically we're going to go as long as possible and we'll gas the bunnies at a certain position when we decide we need to. Right, so when one range is about to run out, that's when we gas the bunnies. And that's exactly the greedy that we're doing here. So that's the proof for why that works. Okay, so how do we do this in some fast amount of time? Because they're n squared ranges we have to check, right? And we don't want problems there. Well, it turns out there are only n log n interesting ranges, or like n log n sets of ranges. So for a particular endpoint, right, if we fix some endpoint and we look at all of the ranges before it, the GCD will only change log n times. And that's because the GCD will only get smaller. So as we go to the left, we introduce new elements. They might decrease the GCD, but they're never going to increase the GCD, right? We already aren't allowed to have any factors other than the ones we already have. So adding new elements, it might keep the GCD the same or it might decrease it. But if it decreases it, it takes away a factor. And that's the only way of decreasing it. And you can only take away a factor log n times. So yeah, the GCD will decrease log n times. So basically what we're going to do is see when does the GCD decrease, and then we'll see like, okay, so the GCD is 7 from the point that the array length is 3 to the time the array length is 10. So for arrays of length 3, 4, 5, 6, 7, 8, 9, and 10, the GCD is 7. That's a problem because when the GCD is 7, and the array length is 7, then you have a problematic range. So that means, since we have a problem, that means we have to kill the rightmost element. And then we'll continue doing that, and now we'll set the rightmost element to 10 to the 9th plus 7, and we guarantee we won't have any problems from that or to the right, because everything to the right of it already works, so this won't be involved in any problematic ranges. I think that makes sense. I hope it does anyway. And I will show the code for it here and kind of explain it with the code a bit more. So yeah, this is a little tricky to implement, to be honest, but here's the idea. Read in the array. Oh, I guess there's one more part I forgot to explain. So hopefully you understand how an RMQ works. If not, I have a algorithms thread video on RMQs. But you can use an RMQ to do range GCD in order very fast. Order 1 to check the GCD of a range with some n log n pre-comp. So yeah, that's what's happening here. That way we only have, I think, only one log factor on our code. So it's going to be n log n rather than n log squared. Okay, so what's happening here is this lift table is for the GCD. So this stores like a power of 2, which is the size of the range, and then the rightmost endpoint. So we'll store the range GCD for all powers of 2 at all rightmost endpoints. There are n log n of those. But what that lets us do is we can find the GCD of any range with this idea. This is the same as the RMQ idea because they can overlap, right? If we have the GCD of this range and of this range, they can overlap, and the GCD of the entire thing is just the GCD of these two GCDs. So yeah, it's the same as like the RMQ idea. So this lets us check the range GCD in order 1, which is helpful. And that's what we're going to do. So we build this lift table, and then if we ever modify something, we will rebuild the lift table. And then we just need to check, like we go from element 0 to element n. If we ever see that this rightmost element that we just added is part of a problematic range, then we delete it. If it's not part of any problematic ranges, then, or like in particular, is it the rightmost endpoint of a problematic range? And if it is, we delete this element. And then any problematic ranges, including this element, will also be deleted. Because we make it 10 to the 9th plus 7. So the question is, how do we check whether something is part of a problematic range now? And in particular, what we do is we're going to look at all of the times the GCD changes. So initially, we have the rightmost endpoint, and the GCD might change in some other position. But we want to see like when it changes, and then it'll be something else for some range, and then it'll be something else for some range, and so on. So yeah, this is what it initially is. Initially, it's just whatever value is there, which is just the value at this position, where this is the rightmost endpoint. And we'll continue checking to see if something is invalid until we hit the left end of the array. So this while loop will run log n times every time the GCD changes. And then each time it runs, we'll see, is this range invalid? So here's what this does. This all runs in order 1, surprisingly, even though it looks kind of sketchy. It runs in order 1 with a GCD call, but if this gets called a bunch of times, that means the GCD will be very small. So I think it is actually order 1 still. But anyway, let's talk about what happens here. So basically, it gets the smallest of the ranges, the biggest of the ranges in the GCD, and it checks if the GCD is in that range of numbers, right? So if the GCD is, like I mentioned earlier, if the GCD is 7 from when the array is size 3 to size 10, 7 is between 3 and 10, which means there's some point where the array size is the same as what the GCD is, which means it's bad. And to do this, we do a binary search to evaluate this part. JK, code is n log squared. Yeah, code's n log squared. So yeah, we have to do a binary search to see when it changes. Yeah, the binary search, we just say, how long is the GCD equal to what it is? So we binary search when it changes next, and then return that. Return the last time that it is what it is. Okay, that's problem D. That's the last one that I coded successfully. But I also think I have the solution to problem E. So I'll talk about that very briefly here, because I think it might be helpful. Distance tree, easy version. Okay, so what is going on here? Yeah, you got this tree, and you're going to add an edge to it of some weight. You want to know for all possible weights that of the edge you could add. For all possible weights, what would be the farthest distance from the root to some other node if you add that edge in such a way to minimize the distance? So yeah, that's the question. So if you add the edge to minimize this farthest distance, for every possible weight of edge you're going to add, what is the longest distance from the root to some node if you try and minimize that? Okay, so yeah, it takes a minute to wrap your head around the problem because there's a lot going on here. But I can discuss the idea real quick. For E1 anyway, I don't know how to extrapolate it to E2. Oh my goodness, they got the tutorial already. Well done, well done. So the idea for E1 anyway is that there are, first, it should be pretty obvious. The edge you're going to add will be from the root to one of the other nodes. Because if you consider doing a BFS on the existing, or maybe even Dijkstra's on the existing edge, on the existing graph, the edge you use is only going to be used in one direction, right? It's not going to be it's not possible that both ends of the edge will be smaller than the other edge. So since it's only used in one direction, you want the end that gets used, the end that's using it, to come from the smallest thing possible. So it might as well come from the root. So you're going to add an edge from the root to one of the nodes. That's what we've just proven there. Not from two non-root nodes. That wouldn't be helpful. So you're adding it from the root to one of the nodes, and you want to do it to maximize the distance from the root to the farthest node after this is added. So what we can consider is that for some tree, we'll have something that looks like this maybe. We got some tree. If we look at let's say this node here is the edge that we add, right? So we're adding this edge here. It's going to be useful in this direction. Each of these nodes will have two possible distances, right? So it's possible that for some node, you're either going to come from this node here, and then from this edge. The other possibility is you'll just come straight from the root. And you'll come from whichever one of those is smaller. So we can make a graph here, which looks like this. On the x-axis, we'll have just the x value, which is the cost of this purple thing. Maybe I'll do this in purple. That way it makes sense. This is just the x cost. And as this cost increases, obviously it's going to either be more, the cost of this path using this purple one is going to be more. So using the purple one, it'll be something like this. Initially, it'll have a cost of 1, right? And then after that, if you increase the cost of the purple one by 1, it'll increase the cost of this by 1. The cost of the black path doesn't care about what that is. So the cost of the black path will be just some constant like this. Now, obviously, you're going to take whichever one of these two lines is smaller, whichever one has the lower cost. The y-axis is the cost here. So what that'll be like is we're going to take the purple part for the first half, and then we'll take the black part for the rest of it. And this will be the cost of this node across all of these possible x values, assuming we pick this node as the other node, or as the one that we have the edge to. So the real question though is, if we put our edge here, what is the farthest node from one of these nodes? So we have this graph here for this node, but we have, we've got some other graph. Maybe it looks like this here. And this second graph might be for this node here. So initially, you can imagine, initially it was closer to this node, but then it will have a higher max value because the max value is equal to the path from this node here. So that's what's happening. And what you want is the maximum of each of these at every x coordinate. So you're interested in the max of each of these at each x coordinate for every node, and then you can just take the best node for each x coordinate. So to figure out which one's the maximum, we can sort each of these things by highest y value, and then we can do a sweep, and then like delete them as we lose them, and look at what's the next one that's still alive. So that's the idea. My code is not totally working, so I'm not going to show it because I might lead you all in the wrong directions here. But yeah, that's certainly one possible solution idea for this. All right, that is all for me. Hopefully the solutions were at least somewhat helpful. And if the round was rated for you, I hope you got a nice rating boost. The tutorial for this contest is already out, so I might look at it after, see why the idea for C is in fact true. But yeah, thanks for watching. Have a great day, and I'll see you in the next contest. Goodbye.